Good morning, everyone. Welcome to this seminar. So today we have the pleasure to welcome Kumar Pranshu from ARIS, Nainital. So he's a senior research fellow working on the liquid mirror telescope for the past 3 years. He's working with the University of Liège and Jean-sur-Dège. So today we'll tell us about the status and latest results from the liquid mirror telescope.
Hello, it's audible, right? Thanks a lot, Dennis, and thank you very much for providing me this opportunity to present the work that we have been doing for the last 3 years now. So, well, in the slide behind me, you can see the observatory of Aries. Here we have 3 important telescopes, and most of the PhD students at Aries spend a significant amount of their time observing using one of these 3 telescopes. The important thing to mention here is that 2 of these 3 telescopes were made possible due to India and Belgium collaboration. And the 2 telescopes are the one in the behind, which is 3.6 meter Devasthil optical telescope, and the one in the front, which is 4 meter International Liquid Mirror Telescope. And you can also see the 3rd telescope, which is a smaller one, but a very useful one, which is 1.3 meter Devasthil fast optical telescope. So here, the numbers 4 meter, 3.6 meter, 1.3 meter represents the diameter of the primary mirror that's used for observing. So the subject of today's talk is the 4 meter ILMT that I have been working on. So on the right side, you can see the side view of the telescope. So it's the dome inside which the telescope is contained. So an ILMT is a liquid mirror telescope, and the main principle behind liquid mirror telescope is that here we use mercury to reflect light instead of conventional glass-based mirror. So the thing with glass-based mirror is that when you try to construct a large-size glass-based mirror for your telescope, it costs a lot, and especially when you try to construct a glass-based mirror telescope that's aspherical, which is usually the case, the cost is even higher. So according to estimates, the total construction cost of ILMT was around 1/10 of a glass-based mirror telescope of similar size. So in fact, the idea is not new. Astronomers over the years have tried to explore this kind of telescope with varying degrees of success. So first real a working telescope, which was a liquid mirror telescope, was worked on by an American astronomer, Robert Wood, in 1909. Then you had one in Canada in 1992, which was a 2.7 meter liquid mirror telescope. Then you had a 3 meter telescope in 1995. And again in Canada, you had a 6 meter LZT in 2003. So what we learned from all these telescopes, what to do and what not to do, were finally implemented in the construction of the 4 meter ILMT. And obviously, the first thing that comes to mind when you look at liquid mirror telescopes is that it can only point towards zenith direction. You can't tilt the telescope to observe any other target, which is, of course, an apparent limitation, but we'll see in this talk that even by just observing the zenith sky, which is a clear sky, with the least amount of atmospheric extinction, you can do a lot of important and useful science. The working principle of such telescope is quite simple. You basically have a big reservoir, which we call the bowl. And inside the bowl, you fill mercury. And what you do is that you rotate the reservoir with a fixed speed. So the mercury, due to the centrifugal force and the force of gravity, it spreads out and covers the bowl and takes the shape of a paraboloid. So you must be remembering from your high school days that if you take a bucket full of water and you rotate it at a constant speed, you naturally get a parabolic surface, right? And thing about parabolic surface is that it can reflect light to a focus. So all the light coming from the zenith gets reflected to a focus where we have the camera, which forms the image. Now, if you look at the shape of the bowl, the ball itself is shaped in uh, a paraboloid shape. So this was made possible using a technique called spin casting, and Dennis was there when this process was taking place. And the advantage of having a paraboloid-shaped bowl is that it minimizes the total volume of mercury required to cover your bowl. In total, we need 50 liters of mercury to cover the bowl and prepare the telescope for observations. The ball rotates at speed of 8 revolutions per minute, so that is enough to focus the light just at the right distance so that we can get to the camera of the ILMT. So the mercury layer that forms over the ball has a uniform thickness of 3 mm. So this ensures that least volume of mercury is needed to completely cover the bowl. So I'll just show you how it looks like in practice. So this is how the bowl looks like. So you see this is a large structure that's covered with mylar sheet. And the reason why I use mylar is, first of all, it prevents the fumes of mercury from escaping the bowl and going outside, which can be toxic, right? And second, this entire bowl will be spinning. So we don't want air resistance to disturb the surface of the mirror and degrade the quality of image. So here what you can see is that there is a nozzle that's transferring the mercury from the container to the bowl. So it takes few hours for the bowl to be completely filled with the 50 liters of mercury. And after the bowl has been filled with mercury, we remove the nozzle, and then we gently spin the mirror. And this is a little tricky process. We have people who are really expert at this now. I tried doing this. I didn't succeed, but there are people who can do it. And if you do it just in the right way, the correct way, you can cover the ball uniformly. So you can see here, the same mercury has completely occupied your bowl. So now what we do, after we have the mercury covering the bowl, we wait for some time, because we want a very thin layer of mercury oxide to form, which further stabilizes the surface of the mercury. And after that, the mirror is finally ready for observations. So just an overview. It's located in Devasthal. It's an optical survey. By the way, it's the first optical survey telescope in India. And it's a zenith pointing telescope. Now the field of view of the telescope is 22 arc minutes. And we use a 4K by 4K CCD camera to observe this field. It can observe in STSS GR and I filters. And see, unlike conventional telescope, we can't track our target. So we needed to use a special kind of imaging process, which is called time-delayed integration. So you might be wondering if during the time when we are acquiring the observation, the sources must be moving over the sky. So how do we get static image? So the way we do it is that the charges that are being received at the CCD are also being transported at the same rate. So effectively, you get a static image. This is called time-delayed integration technique of imaging. We also use an optical corrector just before the CCD to correct for other issues that's related to the telescope. And of course, we had the first flight for this telescope on 29th of April, 2022. So now let's get to the real subject of this talk. Now we have a telescope that's producing an image. So this is how a single ILMT image looks like. This was acquired in STSS I-band. It's a pretty large image. The size of this image is 1.2 degrees squares in terms of the total sky area. And in terms of pixels, it's a rectangular shaped image where the shorter side is 4K pixels and the longer size is 36K pixels. A single image requires 17 minutes of exposure. So in a good night, when the weather is good, and let's say we are observing in winters, and in winters the nights can be long in India, can be up to 14 hours, which still is not as long as nights you get here in winters. So we can acquire up to 35 such images in one single night. Of course, we take small breaks between successive images. So one of the goals of this entire project was to find new sources or transient sources in such image. Now, if you look at this image, you can see there are like plenty of sources, plenty of stars you can already see. So, in fact, according to estimates, a single ILMT image can have up to 40,000 stars or sources. So finding few transients in such image, it's like finding a needle in a haystack. So that was the challenge that we had in front of us. So what we were looking at is to construct some kind of a pipeline that can ingest all these 35 images acquired in a single night and look for transients in each one of those images. And transients can be anything. It can be a supernova, it can be a variable star, it can be an asteroid. So, how should we proceed in this case? The reason why we can do it is that ILMT observes the same field night after night. So we can track the images and look for what is changing, which are the transients. So I'll just get to what I really mean by this. For example, here are two images of the same field acquired on two different nights. On top, we have that image acquired on 24th of October. Below, we have the same field observed on 25th of October. Now, if I straight away asked you, like, find me that's something new on 25th October, which is not on 24th of October, it's difficult. There are like thousands of sources. But maybe if you zoom in closely in every little region of the image, you might find that there is something new on 25th October that's not on 24th of October. So basically, we need some way to compare two images and look for something new. So this is the task, really. Visually, it's very difficult. It's just one image, and we're acquiring 35 such images in one single night. So what should we do? Now, it turns out that a very good technique for finding transients in a data from an astronomical survey is something called an image subtraction. Right? And image subtraction is a very simple process. It's what the name suggests. Basically, you take one image in which you want to find your transient source, and from that, you subtract an image acquired from the same field on one of the previous nights. So what you have is subtracted image. So all the sources which are common in both the images, which are like majority of the sources, will get suppressed, ideally should go away. And whatever should remain behind should be the transient source. So there are like three basic steps that's required to be performed before performing subtraction. First is you have to align the two images. You have to remove your background sky. The point spread function in the two images might be different because the images are acquired on different night with different weather conditions. So you have to match the point spread function, which is typically done using kernel convolution. And once you have performed these basic pre-processing steps, you go ahead and subtract. So I'll just show you an example how it looks like. So here we have, you see on the right side, we have an image acquired on one night, and in the center we have the same field covered on one of the previous nights. So you can see a few stars, and there's one very nice galaxy in the center. So the image in which we want to find transient is something we call the science image, right? And image that we are comparing with, which was acquired on one of the previous nights, is something that we call reference image. And when you see on the right-hand side, we have the result of subtracting the two images. So we basically subtracted reference image from the science image. And you can see all the stars have gone away. The galaxy has gone away. But there's something that has remained as a residual in the center of the difference image. So that points towards some kind of transient phenomena happening inside this galaxy. So in fact, this was a detection of a supernova, SN2024 CJB, using this technique. But we can use the same technique for detecting other kind of transients. So here, in the case of supernova, usually you'll find a galaxy associated with the transient, right? Then you can also detect a variable star using this technique. For example, here, again, you see stars have sort of got suppressed, and in the center you have something bright remaining behind. So this is what will appear in the case of a variable star. And usually with variable star, there is an associated star, not a galaxy, as it's the case with supernova. Here you have a detection of an asteroid. with this using the same method. Now, you might have already noticed that I said that the sources that's common in both the images should completely disappear. Usually this doesn't happen. So here you can see there is these structures in difference image, which are not really transient, but they're still there, which ideally should not have been there. So these are something that we call artifacts. So if we are really looking for a transient source in difference image, the first challenge itself should be to get rid of these artifacts, because these are contaminating our results. So how to do it? Now take this example. Here is a difference image with a lot of artifacts, but there's one nice transient near the top. So this is how typically a transient source would look like, and these are how all artifact sources look like. So we call the transient sources or genuine sources or transients as real sources, and everything else the artifacts here. And we need to have an automated method to distinguish between the two in real time. So it turns out that there is already an existing solution for such kind of problem. From machine learning, there is something known as a convolutional neural network. So what they are basically used is to classify images. For example, you can have a CNN. In short, it's called a CNN. You can have CNN that's trained to distinguish between a cat and a dog. So if you provide that trained CNN with an image of either a cat or a dog, it will produce a score that corresponds to a cat or a dog, right? So this is a very well solved problem in literature. And the way it's useful in our case is that we can simply replace cats and dogs with real and artifacts here, right? So now the challenge is to train a convolutional neural network with lots and lots of samples of real transients and lots of samples of artifacts, artifact sources. And this trained CNN can then be used to distinguish between the two when the data is being acquired in real time. But apart from the output from CNN, we perform some additional thresholdings, like we want to make sure that whatever is the object that the CNN says is a transient should be circular. It should be having an FWHM, which is the full width at half maximum within a reasonable range. And when these two conditions are satisfied, we are ready to say that it's a genuine transient. And of course, like any machine learning algorithm, you need to train a CNN with a data set. So we had to prepare a data set of lots of real sources and lots of artifact sources. And the thing about artifact sources, it's easy to create a data set for artifacts. You simply have to take a lot of subtracted images, and you'll naturally have a lot of artifacts, separate them out, and your artifact data set is ready. But the thing with ILMT was that when we started out this project, we just didn't have enough transient detection. So how to get the real transient sources to train our CNN with? So what we did here is that we know that transient sources are basically point spread functions. So instead of looking for real transients, we simply took out the real stars in our ILMT science images and compiled them in form of a real data set. So in total, the size of the data set was around 5,500 images, equally split into these two classes. And then we went ahead and trained our CNN with that. So this is how data set sample looked like. So on top, we have the around 2,700 real data set samples, which were like basically stars from the images. And below, we had around 2,700 artifacts. The size of every sample is 31 by 31 pixel. So now, after we have the data set, we can train the CNN, and this CNN is now ready to find transients in our difference images. But again, the problem is that we have lots and lots of kinds of transients. We have, like, as I already showed, like we have lots of asteroids, we have variable stars, we have supernova. So we needed some way to classify this transient into some categories. So we thought that we can also use CNN to classify the transients, not just detect them. So this is what we did. So to classify the transient into so we decided to classify our transients into 3 categories, and the categories was supernova-like transients, variable star-like transients, and asteroid-like transients. I already showed the examples how they look like in the real images. So the way to do it is that whenever you find a transient in your difference image, you go back to your reference image, which was used in image subtraction. So if, for example, you can have these 3 situations in your reference image for corresponding to every detected transient. You can either have a galaxy nearby, right? Or you can have a star nearby, or you can have nothing nearby. So from the previous example, we can say that if there is a transient with an associated galaxy, that points strongly to a supernova-like transient. But if there's a transient which is associated with a star, now that can point towards a variable star-like transient. Or when you have a detection that corresponding to which you have nothing in your reference image, that's in most cases it's a likely asteroid detection. So we named these 3 classes as given here. The asteroid-like classes is something that we call hostless candidates. The variable star-like class, we call it point source candidates, and the candidates associated with a galaxy is something that we call extended host-like candidates. So here are a few, also there are associated examples with these defined classes. So now, how can we make use of CNN here? What we can do is that we can just train a CNN that can distinguish between these 3 kind of situations by taking the image from the reference, by taking the context from the reference image. So we trained this classifier with nearly 4,800 images, equally divided into these 3 classes. Divided into 3 classes, and our candidate classifier was ready. So now we have a module that performs image subtraction, a CNN that detects transients in subtracted image, and another CNN that classifies our detected transients into 3 classes. So we can simply put together these 3 modules in form of a pipeline. So the first module in this pipeline is called ILMPdiff, which performs image subtraction. And of course, it produces lots of sources. So basically, we employ a simple source detector to find all the sources in the difference image. Now, every source is transferred into the second module, where we have this CNN-based real bogus classifier, real artifact classifier. What it does is that it accepts all the real transient-looking sources and rejects everything else. Then all the real sources is then transferred to the third module, which is called the NovaNet, which is our transient classifier, alert classifier. So what it does is that, as I already mentioned, it goes back to the reference image, retrieves the context in which the transient occurred, and then it classifies this transient into 3 different categories, which again, as I already mentioned, is extended host, point source, and hostless. Now, in particular, because one of the reasons being because our group is working on supernova-like transients, and also because supernova-like transients require immediate follow-up with other telescopes. We are particularly interested in the extended object-like transients. Basically, we want to find out of all the transients that has been searched by the pipeline, what are the transients which are most likely to be a supernova. So what we do is that we just take aside all the extended object-like sources or transients. Then we perform some additional checks, right? What we do is that we make use of some catalogs to make sure that it's not any other imposter. For example, we make use of a service called Skybot by IMCC to reject cases where the source might be due to an asteroid on a galaxy, so that can happen. We also make use of SIMBAR to confirm if the source is, so if the associated host is a catalog galaxy. So that sort of strengthens our prediction that it might really be a supernova-like candidate. We also make, this we haven't implemented, but in future we are also planning to implement the International Variable Star Index catalog into the pipeline to make sure that whatever we have detected is not actually a variable star that is superimposed on a galaxy. And we also use Gaia to determine magnitude of whatever we have detected. So just to make sure that the host is not basically a very faint, is not actually a star or a. So after making these basic catalog checks, we have a pipeline that's ready for finding transients. So we decided to then we went ahead and deployed this pipeline on ILMT servers. So first we have a computer called CCC1. This is responsible for acquiring all the images. Then all the raw images gets transferred to a workstation 1, where basic pre-processing happens for all the raw images, which includes flat correction, bias, cosmic ray correction, and astrometry. Then all the pre-processed data goes to workstation 2, where the pipeline actually runs. So what happens in workstation 2 is that the pipeline produces a list of transients that gets stored in a database and subtracted images that we can further analyze. And what we do is that in the morning we do a manual vetting of all the transient that has been produced by the pipeline. So this is the distribution of time the pipeline takes to process one single ILMT image. So you can see it takes around 29 minutes to process a single ILMT image. Assuming that on an average, we acquire around 30 images per night, so that translates into 15 hours of total processing time. So which means that if we start our observation at 6 p.m. in the evening, by 9 a.m. next day, we have our results of all the transients ready for us to manually vet and see. So now that we had our pipeline ready, we conducted the transient survey with the help of this pipeline and ILMT. So between November 2023 and May 2025, the pipeline has processed nearly 3,700 full-frame ILMT images. And for every detected transients, it produces an alert that gets stored in our database. In total, more than 23,000 alerts have been generated by the pipeline, corresponding to the detected transients. And the detected transients correspond to a wide variety of objects, which can include supernova, variable stars, AGNs, cataclysmic variables, asteroids, etc. So here is a breakdown of different types of transients that we have detected with the pipeline. On the left-hand side, you have the different categories. In the center column, we have the total number of objects that we detected for that particular category. And on the right-hand side, we have the total number of detections made for that category. So here you can see that there are more detections than objects, which mean that same object has been repeatedly detected multiple times using this pipeline. So in particular, I would like to highlight that we have also detected 21 supernova-like candidates using the procedure that I just described in earlier slides. And of course, apart from that, we have many other types of objects. In particular, we most frequently detected object are asteroids. We have detected like around 9,000 asteroids, almost 20,000 times. So you see, it's very important to have that catalog cross-matching step, because we really want to get rid of all the asteroids before zeroing into the transients of interest. So I'll just have a look at some of the detections that we have made. So here was a transient that we detected on 5th April last year. So here you can see a detection in your difference image, and in the science and reference image, you can see a galaxy. So it appeared like a supernova-like detection, so we cross-matched with catalogs to verify it's not an asteroid. And it turned out that it was not an asteroid, and we went ahead and reported it to the transient name server. So this is the light curve for this object. So this light curve contains both ILMT and ZTF data points. In fact, the structure of the light curve is quite consistent with a supernova-like event. Unfortunately, we could not acquire a spectra for this object, but because the object was little too faint for the optical spectrograph to work. Uh, but regardless of the fact, the light curve sort of shows that it kind of looks like a supernova-like transient. But the way these things work is that unless you have a spectroscopic confirmation, you can't use the word SN in the transient name. That's why it's reported as 80. So here is the report that we submitted for this object, and it was a discovery. Here is another example of supernova-like candidate. Again, just like previous, it's also associated with a galaxy, and you have a detection in a difference image. Unfortunately, we couldn't report this as a discovery because ZTF was able to report it a few hours before us. Here is the light curve of this object. Again, it has this typical rise and a fall, as you would expect for a supernova-like object. Now, this was bright enough for us to acquire spectra, and we did acquire a spectra for this object, this transient event. So you can see that there is a very conspicuous absorption feature at around 6150 angstrom, which corresponds to silicon 2. So you must be knowing that supernova with a silicon absorption line is something known as the type 1a supernova. So here is a list of all the transients that we have reported to the transient name server. These are not all transients we have detected. We have detected more, but these are the ones that we have reported. After the reported ones, 5 were reported as new discovery, and 3 of the reported were actually spectroscopic supernova. Like none of the reported were, unfortunately, none of the transients that we reported discovery were actually spectroscopically verified as well. So that's something that we are looking forward to. So we are not just detecting supernova-like transients. We're also doing plenty of detection for variable stars. So here is an example of detection of something known as long-period variable. So you can see the images below. And here is the light curve of this candidate. And of course, the light curve hasn't covered it seems that the light curve hasn't covered one full cycle. But you can see the extent in MGD is around 120 days, which can happen for these LPVs. Here is, again, an example of an eclipsing binary. Below, you can see the image of detection, your science reference and difference images. And the light curve is a phase-folded light curve of this eclipsing binary. Here, again, is a detection of a cataclysmic variable. Now, we couldn't get a lot of data points for this object because the weather was not really good when this detection happened. But again, if you look at this object, it kind of looks like an asteroid. This is what we thought for the first time, because there's nothing apparent in the reference image. But we detected this same object on multiple occasions, and by cross-matching with SIMBAD, it turned out to be there is a cataclysmic variable at that position, although in its quiescent state, it's too faint to be detected with the ILMT. But in its outburst phase, it's bright enough that we got a detection. So we also find age again. So here is an example of detection of a Seyfert galaxy, and there's a light curve of the Seyfert galaxy. And here is a detection of blazar. Again, we don't have a lot of data points. Bad weather. So one of the most unexpected class of objects that we detected using this pipeline are something known as high proper motion stars. Now, these are not really transients, but what happens is that these stars have a very high space velocity. So the epoch when these stars were observed in the reference image, and again when these stars were observed in the science image, the star had shifted apparently. So due to the shift, we had an excess of flux in the difference image, and that was picked up by the pipeline as a detection. So what I mean to say is this. So you can see here is the star in the reference image has moved relative to the star in the difference image, and that's why it appears in the difference image. And with corresponding to the position of star in the reference image, you have a negative flux, and corresponding to the position of the star in the science image, you have a positive flux. So this was picked up, and when we cross-matched with SIMBAD, turned out that it was a hyperpromotion star. And here is one more example. You can see that there is a very peculiar dipole-like structure for such detections. So this is also one more way how image subtraction-based transient detection can be useful to find such objects. In fact, people have used image subtraction to find hyperpromotion stars in other surveys before as well. Of course, the most frequently detected class of objects are the asteroids. Till now, more than 20,000 detections that we have made using the pipeline were for asteroids, and all these detections correspond more than 9,000 different asteroids. So here is an example of one particular asteroid 2001 OW68, which was detected 23 times with the LMT. Now this is unusual because we don't, as I already said, that we can't really track any object, and asteroids are moving object. The reason why some of these asteroids get detected too many times because they are moving right along the direction in which the LMT is acquiring images. So we went ahead and queried the orbital parameters for this asteroid and plotted generated the light curve for this. So as you can see, there is a systematic rise in the magnitude. The magnitude of asteroids are modulated by several factors, like the absolute distance of the asteroid from the observer on Earth, the distance of the asteroid from the sun, and the angle between the sun and the asteroid and the Earth. So when you correct for these external factors, then you can actually figure out what is the modulation due to the asteroid itself. So after we did a correction for this particular object, and this is how it looks like after correction. So this plot basically represents the reflectivity of the different directions of the asteroids as it rotates while it moves. So also here is distribution of the magnitudes of different asteroids that we have detected using this pipeline. So you can see that most of the asteroids are on the Fentel limit of the ILMT detection threshold. So we see that we have a lot of detections. So one thing that we wondered that how to determine what are the objects that are worth following up scientifically. So basically we are looking for detections which are more peculiar. So one way to define peculiarity can be to determine the rarity of such detections with other surveys. Let's say we detect a transient, but it has been detected a lot of times with other surveys like the ZTF, that it might not be that peculiar. But if we have detected something that has not been detected a lot of times with ZTF or other existing surveys, then it might be more peculiar and scientifically worth following up. So we compiled a list of such objects, and so one important project for the future is to do targeted follow-ups of such objects with ILMT as well as other telescopes at Ares. So here are two examples. On the left-hand side, you have a detection of a QSO, which was not detected many times with ZTA, but its last detection almost coincided with the ILMT detection. So the red vertical line that you see in this plot is the epoch when we made detections with the ILMT. So on the right-hand side, we have one more example of Blazar, where again the last ZTF detection of this Blazar coincided with the ILMT detection. So we also thought that all the results that we are acquiring with the pipeline should be disseminated to public. For that reason, we decided to make a web-based tool called Detection Alert Review Tool. So how this is not online yet, the work is still in progress, but soon we'll be releasing this web tool. So how it looks like. So it will have like two sections. On top, you can basically search for all the transients in a given coordinate. So you can enter your RA index and set a threshold of search. And it will give a list of all the coordinates that were detected within that region. Of course, you should make sure that it should be in your ILMT field of view. And below, we have all the detected transients classified based on SIMBAD categories. So you can like just click one of the symbol category and it will list all the transient detected for that category. For example, you might be interested in studying RL arrays, you just click RL arrays and all the RL arrays will appear. So this is something that people, public can make use of. This is how one particular candidate will look like using this tool. So here is, again, a detection of a supernova. That this is how it appears. On the right-hand side, you have the images, the science reference and difference images, and on the left-hand side, you have all the metadata associated with this detected supernova. Apart from that, we also ask the user a few questions. Does the user think it's a real detection? The answer can be yes, no, or it's a poor subtraction, so it's not. They cannot say for sure. If it's a real detection, does the user think that, what class does the user think it belongs to? So there are the three classes that I already described. The reason why we have these questions is that we can get feedback from the user and assess how the pipeline is performing. And also, we'll use this feedback from the user to make new data sets and train better machine learning models. So here and there is a detection of an asteroid as it looks like in this tool. So of course, there is one challenge that is very obvious with the work that we have done till now. All the data set that we prepared to train our models was synthetic. So as I already mentioned in the start, that we didn't have any real transient data of real transient events to train our CNNs with. So that makes it a problem because any machine learning model trained with an artificial data set is naturally biased towards the person who made the data set. So we thought that, is it possible to fix this problem? So one way could be to use a data from another existing survey which has a large volume of detected transients, and we did that. So that survey, the survey that we chose was the ZTF, and we collected a lot of images from the ZTF and images of detected transients, and we trained a new model, CNN models with that data set, and we fine-tuned that model trained with Z2 data to work for ILMT images. So this technique is quite popular in machine learning language. It's known as transfer learning. And we have tested out this model and it works pretty decent. So in conclusion, I would like to close off by saying that it's a pipeline. PyLMT was successfully deployed on ILMT data stream, and it uses image subtraction and convolutional neural network aided transient candidate detection and classification. Nearly 3,700 images, ILMT images, have been processed with this pipeline. I think should not be 42,000, should be 23,000, leading to generation 23,000 alerts. And we are in the process of developing a transient alert dashboard, which will be a web-based app, web tool that will be available for public to explore all the transients that we're detecting with the ILMT. Transfer learning technique was used to train CNN models for the pipelines. And we published the result recently in MN, and there are 2 more works in progress. These are the references. And this is the wonderful ILMT team that works day and night to make this possible. And thanks a lot.
All right. Thank you, Pranshu. Is there any question in the audience? Many questions. I will start from the front.
Hi, thank you for this great talk. It was really interesting to learn about all of this. So can you say the width of your image strips? What's the width of the field of view?
22 arc minutes.
Sorry?
22 arc minutes.
22 arc minutes. Yeah. Wow, it's relatively thin then. Okay.
So as I already mentioned that so the CCD is 4K by 4K. So the field of view is basically 22 arc minutes by 22 arc minutes. But you see the image is stitched together. So different 22 arc minutes fields are stitched together in one long field. So entire field becomes 22 arc minutes by 9 times 22 arc minutes, which is around 1.2 degrees square of sky area.
So I was surprised by the way that you go, like after the initial detection, you go to a second stage of classification by machine learning, rather, but you still use catalog matching on the side. So, like, what decided you to go to machine learning for the second stage, or rather than go straight to catalog matching?
So I'll give you just one example. For example, sometimes we want to make sure that if it's a supernova like candidate, it might be associated with a galaxy. So for that case, we might use something like a SIMBAD. But the problem is that many bright galaxies are already there in SIMBAD. But for faint galaxies, sometimes you'll find that the object is not cataloged in SIMBAD. So that's why we have to have a CNN-based step to make sure that there is some faint galaxy there. If there is some faint galaxy there, it's able to identify that. But the reason why we also have a catalog, because in case the CNN misclassifies it, and there is a very bright galaxy there, we still have a second option. Right? So that's one purpose. That is one purpose that CNN serves. Second, as I mentioned, that there can also be a case where there's an asteroid coincidentally right at the galaxy. Right? So in that case, again, CNN will classify as a supernova-like event, but when we'll cross-match with a catalog of all the asteroids, then that will get rejected. So basically, both of these two steps are complementing each other to get a result that's more purer.
Thank you.
Yeah, thank you for talk. I have two small questions. So you report on the detection of supernova, on eclipsing binaries and long period variables. So those things are very, very different periods of variability. So how do you cope with that in your choice of reference images? Because also your strip of sky is rotating, it's moving. So how do you cope with that?
Yeah, so typically the target is that once we have a very good set of reference images, we don't want to change it after that. So the sky, of course, the sky that we are observing night after night. So once we have produced a set of reference images, we have our reference image database ready. We log that in, and that can be useful for years. But of course, there will be like, as you said, rotation of the sky due to for the nutations, and so we might need to have new set of reference images years later, but for a period of time when that same reference image can be useful, we keep that.
Okay, then I have another small question if I can. You don't mention satellites. Aren't you annoyed by satellites?
So typically satellites generate streak-like appearances in difference image, and the pipeline is designed as in such a way that it only looks for circular sources. So usually we have a different pipeline that's in progress for detecting the satellite streaks, but this particular pipeline only looks for like circular sources in the difference images.
Hello, thank you for the very nice talk.
Thanks.
I guess the shape of the PSF is very much determined by the shape of the mirror. And so I was wondering, can you say something about the requirements on how constant the rotation speed needs to be in order to avoid time variations in your PSF?
Yeah, so we fix the speed of rotation at 8 revolutions per minute. So that's just enough to get our focus right at the CCD. But sometimes due to variations in temperature, there might be a slight change in PSF. But usually, the variation in PSF is mainly due to the weather from night to night. It's not
the standard deviation on that 8, is it 8.00001?
No, so it's very precise. I don't exactly remember what's the error in this rotational speed, but I think it's precise within reasonable limits, I guess.
Hi, really excellent talk. You may have answered my first question, but I was wondering, what are the different criteria for your transit search part of your CNN that's used to define what's a candidate and what's not? You had already mentioned something about a flux count threshold. Do you also look at like the shape of the PSF? Like what are the different criteria you use?
Yeah, the first layer while searching for transits is of course the CNN. So we have like trained the CNN with plenty of images of real sources and plenty of images of artifacts. Now what we get after this step, we do some additional threshold checks. As you said, we set a certain ratio of FWHMs along X and Y direction, right? And we of course, certain ratio of these FWHM and certain values of these FWHMs, we don't want our sources to be, let's say, greater than 4 arcseconds or less than 1 arcsecond. That's not possible with ILMT, so we reject all these sources. And we also want our sources to have this much of a defined amount of minimum flux value. So we use like these 3 or 4 basic thresholds to further purify the results that we get from the CNN.
Cool, thank you. I have another question too. You had mentioned transfer learning, which I found really interesting. Do you think that the ZTF provides enough data to cover all of the different types of objects that you're interested in finding? I wasn't sure about that.
Yeah, so what we do is that there is a ZTF broker called LRs. So what they have done is that they have very conveniently classified all the transients reported by ZTF into several categories. So while making the data set for transfer learning, we picked out each of these categories, made sure that the data set that we prepared had a representation from all these categories. And then we proceeded with transfer learning. So of course, if there is some category of object that's still not there in ZTF, we can't really do much about that. But we like went ahead and did as much as we can with the data that's publicly available.
Thank you for the nice talk. I have a non-science related question for your website, because the users can click on stuff, but we all know that the internet is not like the nicest place to be. Yeah, so there are bots and people who want to like ruin people's lives. Yeah, so how do you prevent people like or bots clicking like yes or no or maybe or something like this? And how do you filter between user input, which is useful, and like a bot clicking stuff randomly?
Yeah, that's a good question. I never thought about it really. Well, but I'm sure like the astronomy graduate students don't have such malicious intention to click randomly some nonsense. But yeah, there's something that we might have to think about. We haven't, see this website is still not out in public, so we don't know what kind of inputs to expect. Maybe when we try to get such things, then we'll decide something to do about that. Yeah.
Other questions?
Hello. For the first neural network, apparently it was funny. For the first neural network, how many false negatives do you get? How many real things do you accidentally throw out? Because I'm guessing there's some percentage that you accidentally throw out. And when are you happy with that? Are you happy if like 10% gets lost, or is that not acceptable?
So you mean what's the like a recall rate? What percentage of real objects get detected as positive detections?
No, the opposite. How many of real objects do you throw in the bin? Or does your neural network throw in the bin?
So basically, so let's say you have 100 real objects. So how many we successfully recover and how many go?
Yeah, exactly.
So the problem with this is that what we observed is that if the sources are very faint, this percentage of gets thrown in the bin is relatively higher, right? So, but on an average, if considering all things considering well, like if you consider the average magnitude to be around 19.5, the percentage of transients that get recovered is 90%, 90 to 91%. 10% that does go away in the bin. But let's say if you have a real supernova-like event, which will be persistent for several nights. If we don't detect it tonight, we might detect that the next night. So eventually it will get detected. The only thing is that we probably won't be able to report first if it doesn't get detected at the earliest. So it's always good to have a transition that's bright enough, which will be more likely to be detected than not. So this is what we typically wish for. To answer your question, yes, around 90% is something that is a figure that I can say.
Is this equivalent with the training set you used? Like if you check it with the training set you trained on?
Yeah, I mean, that's a problem. With training set, this percentage is a little higher. Because again, as I already mentioned, the reason why we need transfer learning, the training set was a little more contrived in a direction that we decided to make. And as I said, that the sources and training set were stars from the real science images, which are not always very faint. So, no, not the percentage of recurring training set is higher, I would say, than what we actually observe, which we're trying to, the problem that we're trying to solve with transfer learning.
Okay, thanks.
Okay, it's time. Let's thank Pranshu again.